Hi everyone, good morning. So today we are just going to start the lecture with the fundamental concept of electrostatic potential energy. So at first we have to know that what is the potential energy. So if we just revise some of our fundamental concept, then we'll just got to know that potential energy is a sub-classification of mechanical energy. Mechanical energy, that means the energy possessed by the object with respect to its position. That means you can say whether the object is in the state of rest or it is in the state of motion. That is the mechanical energy. Suppose the object is in the state of rest and it has changed its position. So we can say that the object is having some potential energy. Suppose if an object moves in the upward direction and it has traveled some distance or it has traveled some height. So in that case, some potential energy is stored with respect to that particular height. So whenever an object is changing its position and it is in the state of rest, then the energy possessed by the object, that is the potential energy. Okay. So if I'm just talking about a spring, whenever you are compressing the spring, so in that case, some energy is stored with respect to the changed position. That energy is known as potential energy. But in this chapter, we'll just talk about only about the charges. So whenever the charges are changing their positions, so with respect to their position, we can say that how much potential energy can be stored. Okay. So to understand the potential energy, we have to understand that what is electric field. Now this is a positive charge. Due to the positive charge, there is some electric field. Now in that electric field, whenever some other charge are being placed, so obviously it will experience some repulsive force. So at infinity, there is a test charge. The test charge is defined as Q naught, and I will just apply some force on this test charge and I will put that test charge into the electric field. So whenever I am applying the force on the test charge and it is covering some of the distance, so obviously the test charge is doing some work, right? So now the test charge is placed at the boundary of the electric field. So there is a distance from the charge due to which the electric field exists and the test charge. Now that charge that I have placed here, which is positive in nature, let me define it with Q, capital Q. And the distance between the two charges, that is equals to R. So we know whenever any of the charge is brought at the electric field, so obviously with respect to that point, it should have some electric potential. And electric potential is defined by the work done per unit charge, right? So in that case, we can say that the work done in bringing the charge from infinity into the electric field, that is equals to the electric potential multiplied by the value of charge, right? Now, what will be the expression of electric potential? The expression of electric potential is 1 by 4 pi epsilon naught, that is of Q, sorry, it should be of capital Q, Q divided by of R, and it is multiplied by of Q naught. So the total work done, that is the 1 by 4 pi epsilon naught, that is of Q multiplied by Q naught divided by of R. So this is the expression for work done in bringing the charge from infinity into the electric field. Now whatever the work is done, that means the test charge was initially at infinity, now it has changed its position and it has come into the electric field. So due to the change its position, at this point it should have some potential energy. Let me name this point as P. So at the point P, the test charge should have some potential energy. It has done some work already. So whatever the potential energy the charge is having, that is expressed by this expression, that is a 1 by 4 pi epsilon naught Q multiplied by Q naught divided by of R. The expression for work done is equals to the potential energy stored with respect to the position. So with respect to its potential energy, there are a lot of numerical questions are being asked, and today we'll solve all those numerical questions. Okay. Now, now the next topic we are just going to start that work done in rotating the dipole in an electric field. So let me just give the heading at first that work done in rotating the dipole in an electric field. So at first we should draw the electric field lines. Okay. So the uniform electric field lines we are just going to draw here. So these are the uniform electric field lines. So there are the two conditions can exist here. First condition is initially the dipole was in equilibrium position or in equilibrium condition, and the dipole is rotated with some angle of theta. Okay, we are just doing the derivation for this case at first. So this is our dipole. It is having a charge of minus q and plus q. The separated distance between the two charges, that is of 2a, and this is our electric field lines. As you can see that the dipole is parallel with respect to the electric field. So we can say that no torque is experienced by the dipole and no force is exerted on the charges of the dipole. So the dipole is in equilibrium condition. So whenever the dipole is rotated with some angle of theta, then the diagram will be different. I'm just drawing the diagram. So now the dipole is rotated with some angle of theta, but let me at first draw the dipole. This is my minus q, this is my plus q, right? Minus sign is there. The difference between the two charges, that means the separated distance between the two charges, is 2a. Now whenever the dipole is rotated in an uniform electric field with an angle of theta, so the inclination angle can said to be of theta. Now what should be the perpendicular component and what should be the horizontal component, and why we need them? Whenever the dipole is rotated with some angle of theta in an uniform electric field, some force will be experienced by the charges. The minus charge will experience a force of minus q into E, and the plus charge will experience a force of plus q into E. Now the force experienced by the plus charge will be in that direction, and the force experienced by the minus charge will be in the opposite direction. So you can see that the charges are experiencing the force in equal and opposite direction, right? The force is equal and opposite. So whenever some force is experienced by the charges, so obviously they will just rotate the dipole, right? They will just rotate the dipole again. So we should get an expression of torque. So what is the fundamental expression of torque or the moment of force? That is equals to the force experienced by the particle multiplied by the perpendicular distance from the fixed point. In this case, we are just talking about the charges only. So the force experienced by the charges, that is of q into E here. So the expression of torque, that is equals to the force experienced by the charges multiplied by the perpendicular distance. To find out the perpendicular distance, we need the vertical component. So what should be the vertical component? In this way we should draw that one. Now if it is a right angle triangle and the hypotenuse is having the length of 2a, so the perpendicular should have a length of 2a sine theta, because it is having a inclination angle of theta. The inclination angle is same in this case also, the inclination angle is theta. So the perpendicular component we have just got as 2a sine theta. The force experienced by the charges is q into E multiplied by 2a sine theta. So if we just do a small arrangement, this is of 2aq multiplied by of E sine theta. 2aq, that is the dipole moment, because the dipole is look like this. The dipole moment P is given by the value of the charge multiplied by separated distance. So this is of 2aq. So at the place of 2aq, we'll substitute the value of P, and E sin theta will be like that. So this is the torque experienced by the dipole. So whenever the dipole is rotated with an angle of theta, some force is experienced by the charges of the dipole, and they are equal and opposite in nature. So some torque is experienced by the dipole, and due to the torque there is some further displacement. Now in this case I'm not talking about any linear displacement. There should have some angular displacement. Angular displacement means what? Suppose these are my electric field lines, and if the dipole is initially looks like that, if the dipole was initially looks like that, this is my minus q, this is my plus q, and the inclination angle that is of theta. But whenever the both of the charges are experiencing some force, the dipole is experiencing some torque. Due to the application of torque, it is deviated and there is some angular displacement occurred. Now this small angular displacement is d theta. So due to the application of the force or due to the application of the torque, you can say the angular displacement is possible. So it has done some work. So the work done, that is equals to the torque experienced by the dipole multiplied by the angular displacement. So here we'll just integrate this expression and we'll just find out that what will be the final expression of work done in rotating the dipole in an electric field. So whenever we are just integrating on both of the sides, so the limits can be taken as from 0 to w, and in the right hand side it should be taken from 0 to theta. So what is the expression for torque? That is of Pe sin theta d theta, and the limits I have taken from 0 to theta. Okay. Now on both of the sides you can do this integration simultaneously. So integration of dw, that is of w, and the limits is from 0 to w. Pe is actually constant, and integration of sin theta d theta. The limits are from 0 to theta. So P will be at outside integration of sin theta d theta. I have just given you the formula, that is of minus cos theta, and it is from 0 to theta. So Pe, and now the upper limit should be substituted at first. So it is of minus of cos theta, minus of lower limit will be substituted, and it is of minus cos of 0. Okay. So it is of how much? That is of Pe into, that is Pe into minus cos theta, and minus minus plus cos 0 is having the value of 1. So what's the final expression we have obtained? Now in the left hand side, if you just substitute the value of upper limit, it is of w. So the w is having the value of like that. So in the next page, w is equals to Pe into 1 minus of cos theta. Now this is the first expression that we have obtained here. There is the expression for work done in rotating the dipole in an electric field. Now the second condition can be, first condition you can give the heading, you can change that things here, that initially the dipole was in equilibrium position and we have rotated the dipole with an angle of theta. For this condition the derivation is like that, w equals to P into 1 minus of cos theta. But if the dipole is rotated from theta 1 to theta 2, suppose initially the dipole was already inclined with some angle, and now we are just now the dipole has rotated with some other angle, then how to find out the work done? So in that case we'll just use the expression that the work done, that is equals to the torque multiplied by of d theta. So you'll just integrate that one. The work done should have the integration limit will be like that, 0 to w, and in the right hand side it will be from theta 1 to theta 2. So integration of dw, that is of w, and the limits will be from 0 to w. In the right hand side, torque is having the expression of Pe sine theta d theta. The limits are from theta 1 to theta 2. Okay. Now, if we just do this integration, I am just making some small step jump. Integration of sine theta d theta, that is of minus of cos theta, and the limits are from theta 1 to theta 2. So whenever I will just substitute the upper limit at first, it will be minus of cos theta 2 plus of cos theta 1, right? So in the next page, I will just write down that expression by arranging it. But in the left hand side, I'm just substituting the upper limits, and it is of w. So w is equals to p into cos of theta 1 minus cos of theta 2. By this universal expression, you can find out the work done in rotating the dipole in an electric field. Now the final derivation we are just going to do that whenever the dipole is rotated with some angle of theta, before that you have to bring the dipole from infinity into the electric field. That means from the outside of the electric field you have to bring that dipole into the electric field. So obviously there should have done some work, and we have to calculate that work done in bringing the dipole into the electric field. Okay, and we'll get the final expression of potential energy also. So we can give the heading that work done in bringing the dipole, work done in bringing the dipole in the electric field, work done in bringing the dipole in the electric field from infinity, and potential energy, potential energy of a dipole. Now if we just assume that this is the electric field due to a positive charge, this is our electric field. Now this is the dipole, it is having a charge of minus q and plus q, and the separated distance between the two charges, that is of 2a. So you are applying some force on the dipole, and you are bringing the dipole into the electric field, right? So whenever the dipole will be placed into the electric field, it should be placed in that way, right? So the minus q should be like that, and the plus q should be like that. And the separated distance between the two charges, that is of 2a. As you can see in this figure, actually the dipole should be placed in the boundary of the electric field. But whenever I am just placing it, the minus q charge is covering some extra distance of 2a. The plus q charge is at the boundary of the electric field, but the minus q charge has traveled an extra distance of 2a. So the work done by the minus q charge, that is equals to, you can say, I'm just writing down within the small space here, that is of work done by minus q charge, that is equals to the force experienced by the charge. So whenever the charge is in the electric field, so obviously it will experience some force, and it is having a value of minus of q into E. We are just talking about only minus q charge, and it has traveled some extra distance of 2a inside the electric field. So the force experienced by the minus q charge will be of minus q into E multiplied by the distance traveled. In this case, the distance traveled, that is of 2a. So whenever you will just multiply them, what the value will just get, that is of minus q into E multiplied by of 2a. So it is of minus of 2aq multiplied by of E. So in this case, minus of 2aq is the value of dipole moment. So we can write down this is of minus of p into E. So that is the work done by the negative charge whenever the dipole is placed from infinity into the electric field. So we can say that work done by the charge can be stored as a potential energy of the dipole. So the expression or so the expression for potential energy, that is of U naught, you can say, that is minus of P into E. Okay. Now there should be a question, sir, why you are just taking only minus Q charge? Because if you are seeing the diagram that the plus Q charge is at the boundary of the electric field, but the minus Q charge has covered some extra distance. How much? It is of 2A. So the work done by the minus Q charge, that is equals to the force experienced by the charge multiplied by the extra distance traveled. So in this case, whatever the work is done by the negative charge, that is stored as a potential energy with respect to its position. Now, in the previous case, we got an expression that initially the dipole was in equilibrium position, and whenever the dipole is rotated with an angle of theta, so there the work done by the dipole, I have to write down so long, work done by the dipole in rotating it with an angle of theta, work done by the dipole in rotating it with an angle of theta is W equals to PE into 1 minus of cos theta. Okay. So initially the dipole was in equilibrium position. Now we have just rotated the dipole with an angle of theta. So this is an expression for work done. So what should be the total potential energy stored by the dipole? The expression for total potential energy stored, that is equals to the expression for work done plus of the expression for potential energy stored by the negative charge. So in this case, what is the expression for work done? That is of PE into 1 minus of cos theta plus of U naught. What is the value of U naught? That is of minus PE into E. So if you just calculate what the expression I will get, I'm not doing the calculation more because I don't have the space. So after doing the calculation, the final expression I'm getting as minus of PE cos theta. Okay. So this is the expression for potential energy stored by a dipole, that is of minus PE cos theta. So in the next page, so U equals to minus PE cos theta. Now do you remember some property of vector? That means of A dot B equals to AB cos theta. So we can say that PE cos theta, sorry, minus PE cos theta is minus of P dot of E. So this is an expression of potential energy stored by the dipole. After that, we have to study some of the numerical question of it, that how much kinetic energy is gained by an electron which was initially at rest, but when it is moved through a potential difference of 1000 volt, you have to find out the kinetic energy. In this whole chapter, we didn't have got any expression that relates the kinetic energy and potential difference, but whenever the electron is being accelerated, but when, or you can say whenever the electron is being moved in an electric field, so as the electron is moving, so it should have some kinetic energy, that is equals to the value of the electron multiplied by the potential difference. Now what is the charge of an electron? That is 1.6 into 10 to the power minus 19 coulomb multiplied by, what is the potential difference here? The potential difference is 1000. 1000 means how much? 10 to the power 3. 10 to the power 3 into 10 to the power minus 19. That means 10 to the power minus 16. That joule. Kitna आसान है, right? And you guys are thinking that numerical question from physics, obviously it will be hard. Now, three equal charges of 5 microcoulomb each are placed at the three vertices of an equilateral triangle. So we have to make an equilateral triangle at first. This is our equilateral triangle. Now three equal charges of magnitude 5 microcoulomb. So this is 5 microcoulomb, this is also 5 microcoulomb, and this is also 5 microcoulomb. And the separated distance is 5 centimeter. The equilateral triangle is having the property that all of the sides are equal, so I don't have to write down the separated distance for each case. We have to find out the electrostatic potential energy of the system of charges. You know the expression of electrostatic potential energy of the system of charges. That is of U equals to 1 by 4 pi epsilon naught Q multiplied by of Q naught divided by of R. Remember this expression? At the beginning of this class we had done this. So we'll just find out the electrostatic potential energy for the system of charges. Now, this point is A, this point is B, this point is C. So what will be the final expression of electrostatic potential energy? That is equals to the electrostatic potential energy between A and B, the electrostatic potential energy between B and C, and the electrostatic potential energy between C and A. So in all of this expression, one thing is common, that is a 1 by 4 pi epsilon naught. But we'll just take it common after this line. So in the first line, what will be the value of U of AB? U of AB, that means the potential energy between A and B, that is of 1 by 4 pi epsilon naught 5 microcoulomb. What do you mean by 5 microcoulomb? 5 microcoulomb means 5 into 10 to the power of minus 6. So it is the 5 into 5. There are two 10 to the power minus 6. So I'm just directly write it down 10 to the power minus 12. Okay. For this 5, I will get 10 to the power minus 6. For this 5, I will get another 10 to the power minus 6. So I'm just writing down 10 to the power minus 12. Divided by the separated distance, that is of how much? 5 centimeter is there. So it is a 5 into 10 to the power of minus 2. So 1 5 is getting eliminated, right? On this is a 1 by 4 pi epsilon naught. I will just do nothing in this case. That 1 by 4 pi epsilon naught will be like that. 5. This 10 to the power minus 2, which is in the denominator, it will just go up and it will become 10 to the power plus 2. So it is 10 to the power minus 12 into 10 to the power plus 2. It will be how much? The final expression I'm just getting as 1 by 4 pi epsilon naught into 5 into 10 to the power of minus 10, that joule. Now the electrostatic potential energy due to A and B, the electrostatic potential energy due to B and C and A, all these three values are equal. So you can say this is equals to U of AB multiplied by of 3, right? कोई एक का पोटेंशियल एनर्जी निकाल के उसको 3 से मल्टीप्लाई करने से मिल जाएगा, बार बार लिखने का क्या जरूरत है. Now U of AB, that is of how much? 1 by 4 pi epsilon naught, that is of multiplied by 5 into 10 to the power minus 10 multiplied by of 3. So 1 by 4 pi epsilon naught, this is the 9 into 10 to the power of 9 into 5 into 10 to the power of minus 10 into of 3, right? So how much you are just getting? 5 3s are 15, 15 9s are 135. So 135 into 10 to the power minus 1. 135 into 10 to the power minus 1, that means 13.5. So the final answer is 13.5 joule. Okay. These are the these are the ISC previous year questions. That's why I am discussing. They have already come. Now the next question. Two positive charges. No, this question I will not solve. This question is your homework. Every question I will not solve. This question is your homework. Practice all of the numerical questions from this chapter. If you feel any doubt, just contact me.